So in our last couple of videos, we talked about how to take a sample and find its mean and then use that to make some inference about the overall population. So our example was if I want to know what is the average age of every coin in the United States, or if I wanted to know what percentage of every coin in the United States is pennies, I might do a sample. Here's my sample right here of all of this loose change. This is my sample, and I could find the average of the sample. And assuming the sample's really good, that should be a reasonable estimate for the entire population. Let's say I find the average age of a coin in here is 22 years, for example, and I find that 18% are pennies. Great. Now, there's something called sampling error, which is there is an answer out there. There is an answer to the question, what is the average age of a coin in the United States? We don't know what that is, but there's an answer. Our answer from our sample, the average of this jar of change, will always be different from the actual answer for the real age of every coin in the United States, because this isn't every coin in the United States. This is just a subset of them. And no matter how good my sample is, no matter how careful I am to avoid sources of non-sampling error, I'm still going to have a little bit of difference between what I found from my sample and the real population. And we call that difference sampling error. It is unavoidable, but we can figure out how big it is. We can know how big the sampling error is. So I can say, well, yeah, the average age of every coin in this jar is 22, and that means that the average age of every coin in the population is between 21 and 23, or 20 and 24, or 0 and 44. I want to have a sense of what the range is for where I think the real population falls, and that's where I need to estimate what the sampling error is. So method number one to do this, the gold standard, don't do one sample, do many, do a dozen, 2 dozen samples, all with the same sample design. Remember, at each stage in your sample design, you're doing some kind of random selection. Randomly select the days of the week to go, randomly select who to talk to, randomly, systematically choose the coins out of the cash register, whatever the case may be. You can run that sample again. You'd end up with different days, different stores, different people to talk to, and different coins out of the cash register. So you will get a different sample and a different result. Do that a couple of dozen times, and you can actually have a bunch of averages, and then you can say, how much do they tend to vary from each other? So our steps last time is you do all those samples, you find the mean, if it's numerical data, or the proportion, if it's categorical data, what proportion are pennies, of each one of the samples. We treat that big list of means or that big list of proportions as if they are the data. Those are now the numbers we're concerned with. We find the average of those averages, or the average of those proportions, and we call those the mean of the sampling distribution. The average of the average is mu subscript x bar, average of sample means. The average of proportions is mu subscript p hat, average of proportions. We also critically find the standard deviation. How much do those samples tend to vary from each other? If it's numerical, it's sigma sub x bar. If it's categorical, it's sigma sub p hat. So we find the average and standard deviation of all of those different means or all of those different proportions. We then know what the middle value is, what is the proportion we are most likely to get, and how much do we tend to vary from that by, and that tells us the sampling error. That tells us how much each sample differs from each other, which is also a pretty good benchmark of how much each sample probably differs from the real answer, from the mean. Then we construct what are called confidence intervals. If we start with that mean in the middle, that sampling distribution mean in the middle, and we take that standard deviation, we remember this from way back in January, within one standard deviation of the mean, you should find 68% of the samples. So we say we're 68% confident that the true average falls within one standard deviation of the mean. Within 2 standard deviations, we're 95% sure. Within 3 standard deviations, we're over 99% sure. So we can give a range that is wide and be really confident that the real average is in there, or we can give a range that is tight and be less confident. And it depends on what our purposes are and why we conducted this. But that method sucks. And it sucks because in order to make that method work, we've got to conduct like a few dozen samples. Sampling is expensive. Sampling is time consuming. Sampling takes a lot of resources. This is not actually how people do it because it's the gold standard, but it's really hard to do and really expensive. So we really want as a way to estimate this using only a single sample, not many samples. And that's what this slide shows all about. So first of all, if I've got a single sample, it has an average or a proportion. If it's numerical, like the age of these coins, it's got an average. If it's categorical, like is it a penny or not, we've got a proportion. Whatever the sample average is, or the sample proportion is, that's going to be the best guess I can have for what is the average of the entire population. So the average of the sample is approximately equal, as best as we're going to get, to what would have been the average of the sampling distribution if we'd done many samples, which should be a reasonable approximation of the true average of the data. Similarly, the proportion, say what percent are pennies, is close to what the average of all the proportions would have been if I'd done a ton of samples, which should be close to what the actual proportion of pennies is in all coins in circulation in the US. So in other words, the average and proportion of our sample, that's our new center value. It's the best we're going to get. It's not great, but it's the best we're going to get. What about the standard deviation? Well, we have these wacky formulas. These formulas do a pretty good job of estimating what the standard deviation of the sampling distribution would be. In other words, they estimate how much each sample would vary from the middle by in general. They're super weird. Don't spend a lot of time thinking about where they came from, but they work pretty well. If it's numerical data, we take the standard deviation of the sample and divide it by the square root of the size of the sample. Standard deviation of the sample divided by the square root of the size of the sample. And then what that does is, the lower the standard deviation, in other words, the less each coin in this jar varies from each other coin, the more confident I can be in my sample. The bigger the size of the sample, the more coins that are in this jar, the more confident I can be in my sample. Those two things both bring the error down. Data that are less varied to begin with, data that are closer together, and more data. Those are the two things that help us out here. For categorical data, you do P, which is what percent of coins in this jar are pennies, times 1 minus P. In other words, what percent are not pennies, right? If P is 0.15, 15%, then this is 0.85, 85%. Divide it by, again, the number of coins in the sample, and for bizarre reasons, square root that sucker. So what this does is, the closer that the proportion is to 50-50, the closer these two both are to 0.5, this allows us to get a lower standard error, be a little bit more confident. And again, the more coins in the sample, the more confident we can be, and the lower standard error we'll get. One huge caveat to this. This assumes that the sample size is at bare minimum 30. If it's not at least 30, this doesn't really work. It's got to be bare minimum 30. And if it's categorical, we have an additional requirement, which is at least 5 in each category. It means at least 5 things that are what we're looking for, say pennies, and at least 5 things that are not what we're looking for, not pennies. So if I looked at this jar and I had 30 coins and 26 of them were pennies, this doesn't work because I don't have at least 5 non-pennies. So those are the two bare minimum requirements, and more is better. Let's do an example. Say I've got one sample of 400 coins, and the average age is 22 years with a standard deviation of 10 years. Most coins are within 10 years of 22 years old. They're between 12 and 32 years old. Throw this into the formula. So I've got my average of 10 divided by the square root of the sample size divided by square root of 400, which is 20. So I get a standard error for the years of 0.5. If 15% of the coins are pennies, I throw that into my formula, 0.5 times 1 minus 0.15, times 1 minus 0.15 divided by 400 square root, I get 1.8%. So I can now say that I think a pretty good guess for the average age of a coin in the US is 22, which again is the average of my sample, plus or minus 0.5, plus or minus about half a year. And I think that about 15% are coins, which again is what my sample saw, plus or minus 1.8%, which was my standard error. And if I want to throw that into a confidence interval, it would look like this. 68%, again, these first three are for age. I start with my average of 22 and I add or subtract one standard error. I add or subtract 0.5 once. I'm 68% confident that the average coin is between 21 and a half and 22 and a half years old. 95% I do 2. That's 21 to 23. 99% I do 3. I'm 99% confident the average age of a coin in the US is between 20.5 and 23.5. This is exactly like we did on the last assignment, exactly like the last couple slideshows, except that instead of getting the standard error from the standard, standard brain fart deviation, there it is, rather than getting the standard error from the standard deviation of the sampling distribution, we get it from this weird formula. For the categorical data, again, my average was 15% because I said 15% of the coins in that jar were pennies. My standard error, based on this formula, was 1.8%. So I'm going to start at 15%. If I go 1.8% in both directions, I get to 13.2 and 16.8. I'm 68% confident in that. 2 standard deviations, 2 times 1.8. Now I'm at 11.6 and 18.6. I'm 95% confident in that. Throw in another one, 3 standard deviations, and I'm 99% confident that between about 10 and about 20% of the coins in the US are pennies based on this. That gets you through the front page of the assignment. Next video will take you through the back page.